Your voice is not audible.
Yeah, no, I will say no. So, good morning to everyone present here. So, for the second session day of this online STC on computational methods and analysis for engineers, organized by Department of Chemical Engineering, NIT Jalandhar, and convener of the course is Dr. Anurag Kumar Tiwari, and patron and head of the department is Dr. Sangeeta Garg. I am the coordinator of this particular course. So this is the second day of our course actually. So the first session would be started by Dr. Senthilmurugan. So let me introduce Dr. Senthilmurugan to all of you present here. We have amidst us Dr. Senthilmurugan, uh, who is an associate professor at the Department of Chemical Engineering, IIT Guwahati. Uh, Dr. Murugan completed his PhD and MTech from IIT Delhi. Earlier, he pursued his BE from Bhartiyar University, Coimbatore. Prior to joining IIT Guwahati, Dr. Murugan was enriched with 8 years of industrial research experience, focusing on water and wastewater treatment, industrial process water, sustainable water recycle, power, renewable, and oil and gas sector. Dr. Senthil has to his credit over 20 plus research projects which are executed 19 patents, 48 journal papers, two contributions in industrial magazines. Uh, he also presented 30 conference papers. Dr. Morgan won the H2O Water Energy Nexus Award in the year 2010 for the RO performance monitoring and optimization solution. He was also awarded ABB Platinum Certificate of, of Appreciation in year 2010 as a best individual researcher for the implementation of model-based membrane performance monitoring solution. Prior to that, he was awarded ABB Certificate of Excellence in year 2009 for best teamwork. He was also bestowed the Dr. K.S. Krishnan Research Fellowship by the Department of Atomic Energy (DAE) on behalf of the President of India in the year 2005 to 2006. Dr. Senthil Murugan has monitored 8 UG, 5 masters, 14 PhD students who are working on industry funded project worth rupees 6.5 crore. So with this short introduction, now I would like Dr. Senthil Murugan to conduct the session. Over to you, sir.
Yes, you forgot to say that we did it MTech from we did it.
Yeah, I will say that now. So Dr. Murugan and we are classmates at IIT Delhi. So masters we did together, and then I moved to IIT Bombay, and he continued his PhD at IIT Delhi. So uh, yes, Dr. Murugan, you can conduct the session now.
Yeah, thank you.
Yeah, welcome.
Hope you are able to see my screen now.
Uh, yeah, it's coming.
Yeah.
Yeah, it's visible.
Good morning to all. I want to know what is the audience proficiency in this. Are they all are chemical engineers? Are they are from
Yeah,
someone?
they are mixed actually. So most of them are chemicals. So they are
So how many of them
mixed
are?
from academy, from industry also.
Yeah. Okay. So anybody is without bachelor's in chemical engineering or food technology, let me know, because I'm talking more about membrane processes. But anyway, optimization is generic, but membrane processes is more specific to some extent to chemical engineering. If you have any clarification, let me know. I'll stop me. I'll try to maybe educate in a better manner. Okay. So I don't need to give a more introduction. So we have already seen about me. My friend Raj told more about what I do. So let me jump into directly to the subject. we are talking about, today overall membrane separation processes, and how do we design these membrane separation processes for water, wastewater, and other applications which we are going to see. So in general, when we say membrane, membrane is a semi-permeable polymer sheet that allows water, and then it separates the solute molecules. When we say solute molecule, anything bigger than the water molecule size. So, for example, ions, molecules, all the small particles, it can separate from the membrane. So the process can vary from microfiltration, ultrafiltration, reverse osmosis, and in between you'll have a nanofiltration. But these processes are basically on the size of the particle which can reject by the membrane. If the size of the particles are in the ionic level, then we call it as the reverse osmosis or nanofiltration membrane. But when we talk about the particles which are in the order of few nanometers to micron, so we call it as some extent a nano and ultrafiltration, and then anything in the micron level, then we call it as a microfiltration. So that's the basic separation which we can identify. But today I will be more focused on osmotic-based process, because there is a well-established methodologies are available for modeling and optimization for ultrafiltration and microfiltration. But when we talk about the osmotic process like forward osmosis, pressure-assisted osmosis, and then pressure-retarded osmosis, PRO, and then the reverse osmosis. So we would like to have a quick overview what is the process, and then how to model this process, and how we can apply that model for optimizing the overall process. So what is forward osmosis? So where we have a driving force is the osmotic pressure difference between the fresh water and seawater. So in this case, we have the fresh water, and the other side we have salt water, which could be seawater, which is higher salt concentration. So due to the difference in the salt concentration and water concentration, so the water will be moving from higher concentration to lower concentration side. So when I say water, I'm talking about the water concentration. If you talk about the salt concentration, the water will be moving from low salt concentration side to high salt concentration side, so which is equal to this. So the water will be moving from higher concentration to lower concentration. And then similarly, in a pressure assisted osmosis process, we apply an external pressure along with the osmotic differential force. We have a delta pi, along with we apply a delta p that will increase the flux in addition to delta pi driving force. So which means that if we need more flux, then we need to apply a delta p, the differential pressure, which is equal to P1 minus P2. The P1 is in the fresh water side, and P2 will be in the salt water side. So this we call it as pressure assisted osmosis. So basically, we are giving further assistance of through pressure to increase the flux. That's why we call it as pressure assisted osmosis. Still, it is osmosis, where water is flowing from the high concentration to low concentration side. And similarly, in a pressure retarded osmosis, we apply a pressure in the opposite side. So what is the meaning for opposite side? We apply in the seawater side. But still, the driving force is going to be delta pi minus delta p. So why? Because the delta p is going to restrict the water flow which is coming from the fresh water to seawater. So it means that we are going to apply a delta p. However, the delta p is going to be less than the delta pi. It is going to be less than the delta pi, so that still water will be flowing from the fresh water to the seawater. However, we are applying the pressure. So because the delta pi is greater than the delta P. So why it is important? So here, we are getting a more water, so we can think of, concentration and many applications. But here, why we should apply a pressure and why we should restrict the water flow. So basically, we say that the pressure retarded osmosis can help us to produce the energy from the seawater. So what does it mean? The seawater is at high pressure, and this water can be passed through a turbine, and that turbine can generate the electrical energy. So this is, we call it as a pressure retarded osmosis. Now, the next level, if you increase the pressure still further up, if you increase the still pressure further up, where the delta P is greater than delta pi, so then what will happen that the osmotic equilibrium is getting stopped. Our osmotic equilibrium is getting break. So because of that, the water will be flowing from seaside to the fresh side. So this we call it as a reverse osmosis. So in the osmotic process, we have a forward osmosis, pressure assisted osmosis, pressure retarded osmosis, and then reverse osmosis. If you look, a reverse osmosis is well established, and it's not something new which is exist in 80s onwards. So if we look into a technology-wise, it is very well matured, but these technologies like a forward osmosis, pressure-assisted osmosis, and then PRO is not matured enough. It is getting developed and it is getting adapted to industry to make use of the technology. So if we look in the application side, the forward osmosis is used for concentration applications. When we say concentration application, food processing and pharma application, and then the desalination and water treatment, wastewater treatment. So the tea concentration and then sugarcane juice clarification and concentration. These are the two applications where we have focused in our lab, water and energy lab. Two of my PhD students are working. So I will touch upon how, which we can use it. So apart from that, how we can use the FO and optimization also. So how process can be designed for a given application. How do you design a forward osmosis process? That also I will be covering in today's class. And then the pressure retarded osmosis, as I said, which is mostly widely used for energy generation. But however, if we integrate in such a way with the FO or membrane distillation, it can be also adapted for wastewater treatment and also for desalination. So that is also I will be talking in this course. So the next one, liquid food concentration. So when we talk about the liquid food concentration, why we should concentrate? So what do we mean the liquid food concentration? You take any juice or any liquid food which we come across. So they are packed and they are transported from for long distance, and also it needs to be preserved when it is not available. So seasonal fruits, so we need to concentrate them and then we need to preserve them. So for that application also, the liquid food water content has to be reduced. So how do you reduce the water content? So one application is that we can evaporate. And if you evaporate, the juice can degrade. The degradation of the juice is more viable. So to avoid that, the forward osmosis is one of the alternate process where we can concentrate the fruit juice without heating. That will ultimately end up in reducing the packaging cost. If you want to store the raw juice, then it may be taking more than a liter volume. But if you concentrate them, then that becomes 100 ml, less than 100 ml. So that's the one of the packaging cost. And then the correspondingly the transportation. So we need to do the transportation, and the transportation cost is also going to reduce. And then storage. So we need to keep them under a sub-zero condition, some of them. So if you have a more volume, then the latent heat and the sensible heat, is going to be huge. So we need to remove huge amount of heat. So from that angle, the concentration and then transportation and storage and packing is going to give huge benefit for the industries. So ultimately, that will increase the shelf life, water activity, transportation cost, and then packing cost will be reduced. So when we talk about the application of food concentration, so one is the food processing, like you see the juices, all the juice, where we need to concentrate. The another side is that the pharmaceutical applications, where in the pharmaceutical application, so we need to concentrate the drugs, so that the concentrated drugs can be crystallized and it can be fabricated, manufactured as a tablets form. And then we have beauty and skincare industries, like all your aloe vera juice. There are so many things which we use in the beauty and skincare industries, which needs to be concentrated. And then the edible packing, as usual, we have all the edible items, so that also can be concentrated and then that is packed. So coming to conventional technologies, as I said, evaporation, freeze concentration, and then we can also look into a reverse osmosis process. So in the reverse osmosis process, what happens that the fouling is one of the limitation factor, and also the osmotic pressure. So what happens to the osmotic pressure is that when we have high concentrated juice, so the osmotic pressure is going to be a limiting factor to push the water from juice to the other side, because the reason is that the pressure requirement for the reverse osmosis will be very high, and design of the components that can withstand such a high pressure is going to be a limiting factor. So for example, today we have the membrane and the modules that can withstand up to 80 bar. But if your osmotic pressure is more than 80 bar, then that's going to be a trivial solution where we don't have components at low cost. Then the freeze concentration, of course, it works well. Many food industries are using, but the cost of the energy required for freezing is going to be very expensive, and then the technology is also very expensive, and scalability is another big problem. Like if you want to scale up for a huge volume, then that's going to be a kind of a challenging job. The next one is that, as I said, forward osmosis is found to be one of the alternative and attracting process for fruit juice application and concentration. But it has also some limitation, but that limitation is being addressed by many researchers and also in the progress of addressing. So one is that the low fouling propensity. So earlier days, many of us claimed that the forward osmosis is supposed to give low fouling propensity. There is a recent article in a Journal of Membrane Science in 2020 October, where they have proven that if you have a constant flux, let's say you have a reverse osmosis and you have a PR, pressure retarded osmosis, and then you have a forward osmosis. In all these processes, if we try to maintain the same flux per unit membrane area, it means that the water flow through the membrane per unit area. If we maintain a same flux, then they observed that the fouling potential for FO membrane is found to be much higher than the other three processes, because of the support layer issues. The support layer has the internal concentration polarization, and that result into a very high concentration polarization, and that will result in a permanent fouling. So which is impacting much higher than the any RO or NF membrane. So this was supposed to be a big climb for forward osmosis, but that is not exactly the answer now. Further research is required to conclude more better manner. Of course, still people believe that the low fouling propensity is one of the added advantage for forward osmosis, but now it is questioned. This year only it is questioned: is it giving really a low fouling propensity? And then the high rejection of solutes, and then reduced energy consumption. So the high rejection of solutes. So I said, since pressure is not applied, the rejection is expected to be very high. And since we are not using high pressure, so the energy consumption is less. However, I will be explaining you in the later part, we will be using a draw solute. The draw solute recovery and regeneration plays a critical role. If we have a small draw solute, then the energy consumption will be low, but otherwise it's going to be very high. Then it can operate at ambient temperature, as I said, not like a thermal process, which is going to give an added benefit. So that helps to preserve the quality in terms of color, flavor, and sensory quality, basically the taste of the final concentrated product. So the challenges, as I was telling earlier, the availability of easily recoverable draw solute. So I'll be teaching you what is draw solute in later couple of slides. So the draw solute is a solute which we use it for as a concentrated solution. So in my previous picture, so I was explaining you here in this picture. So the concentrated solution, that is basically a draw solute, and this we call it as a feed solute. So the availability of this draw solute, then recovery is going to be one of the critical and important process. And then the availability of food grade draw solute. So the thing is that when we are going to concentrate a juice, the draw solute should not come into a liquid food. If it is coming to a liquid food, then that's going to be a challenging task, which is going to create a big problem. And then the availability of a low energy consumption draw solute recovery mechanism. That's what I was telling you. How can we regenerate the mechanism? These are all some scope where many people are working on. Let's assume that this is being addressed. Now, how we will design a forward osmosis process. That's what I will be talking about today in remaining part of the class. So if we talk about the ideal condition for liquid food concentration, the preferable operating condition for is low temperature, optimal pressure, and then optimal pH. And then the suitably, we should be able to go for a large scale continuous production. So the process should have the ability to scale up for continuous production. And then the economics. So ultimately, any process to have a sustainability, we should have a good economic benefits. So when we say economic benefit, the low energy consumption, and then we talk about good quality of the product and consistency. So I will talk about today, there are two applications. One is a tea, another one is a sugar cane. So if you talk about the sugar cane applications, it is basically one of the important feed for many applications. So you can see that the per capita sugar consumption in top 7 countries, approximately 57.6 kg per capita, particularly in Brazil. The Brazil is one of the highest sugarcane producing country, because they use for ethanol production. So they produce a huge amount of ethanol from sugar. So they consume a huge sugar. And then we can see that India is 18.6, which is far away. So if you want to really produce ethanol from sugar, then you need to increase your sugar production. So that requires smart technologies, and then process like forward osmosis. So similarly, tea, why we should concentrate the tea? Most of us, we know that the concentration of tea is a very important process in food industries. If you talk about the Hindustan Unilever or Tata Tea, so what they do that the tea is plugged in, and then they do a fermentation, and then they try to add more flavors. So what is those flavors? Basically the antioxidants. So you have to add polyphenolic components and theophylline, and these are all antioxidants, which is very good for human health. So what they do that they try to extract from the tea these antioxidants as a liquid fluid. Then they will be adding in the raw tea so that the tea will have required amount of antioxidants. So it means that if you want to have a consistent tea quality, so let's say today somebody is buying from tea from Assam, tomorrow from another estate, so the quality of the tea will be varying, but what is packed for our home, the quality should not change. So what they do that they extract the antioxidants and then flavor, and they try to add in addition to the what is exist in the tea, so that the quality of the tea which we get is consistent and they will maintain. So that's where they are looking for a concentrated tea that can be used to maintain the quality of the tea leaves which we get it in our home. This is one application. The another application is that after some years you may not use the tea leaves. Everybody will use a tea liquid. The concentrated liquid, you can add a small spoon of tea, and that can be used for preparing the tea, like what we do for a milk. Adding like a milk, you add 1 spoon of tea solution. So that's where we are talking about the concentration and defined as a controlled removal of water. And then the controlled removal of water from the aqueous food helps reducing the water activity. So there are some food where water activity leads to a degradation of the food. The efficient dewatering process ensures the product stability and even significantly reduces both manufacturing and transportation costs. That's what we have seen. So this is the typical process available in the field, where evaporation, freeze, concentration, and membrane based like RO, UF, pervaporation, and membrane distillations are widely used. But we are talking about something new. Now, this is an introduction for the forward osmosis and membrane process. So let me know if anybody has any doubt in this. So let me stop here, because I will be jumping into now how do we design this process. Any questions? Anybody has doubt?
Forward osmosis is food materials. You're saying that you can concentrate it. So you will put it in a liquid which is of higher concentration, right?
Yes. So we have to use the liquid which is higher osmotic pressure. It is not necessary that higher concentration. It should be higher osmotic pressure.
Okay.
Any other? Yeah. So next we are talking about how the modeling and simulation is going to help for building a process, or design a process. So in general, if we talk about, the model is used for many applications. So example, we look modeling as a core for operational assistance, scheduling, simulation, optimization and advanced control. So where, you have a process, if you want to have operational assistance, then we need a model for the process. And then production planning, and then, safety management, and then maintenance management, and then the MES, basically the manufacturing and execution system. So we have a control domain, we have a business domain. Apart from this, if you want to design a process, basically a process engineering. So where in the process engineering also, we need a mathematical model of the process. So if you decide, okay, we are going to design a process, then we need a model. But what basis we will develop a model? So what is the basis for the development of the model? So what we need to first realize that, what is the objective for our model? So what is the objective for our model? It's like experience the reality. So what is the goal of the model? So, and then the management objectives. So what is management objectives? What is experience reality? So example, I want to design a process for 100 liter per hour capacity of concentrating the liquid fruit juice. Now this is a management objective. So they have given. Then what is the another management objective? He will say that my process cost should be, the processing cost of the juice should be less than 100 rupees for 1000 liter or 100 liter. So per liter 1 rupee. So it should not be more than that. So if it is more than 1 rupee per liter, then that's not going to be affordable for us. And then based on this input, so we can formulate objectives. What is experience reality? So what is experience reality? Let's say today you are defining 100, but tomorrow the business is doing well, and that will result in requirement of higher quantity of juice production. Does this process is scalable? Is it scalable? Is it viable to increase the capacity with minimal change? These are all experiencing the reality. It should not be the hardcore constraint that you design a process and that cannot be further taken up. So these are all the inputs which will be coming from the objectives, management objectives, experience the reality. And then with that, we will try to formulate the model. So where we need to identify key variables, and then what kind of a physics behind it. Let's say if you talk about the membrane process, so the mass transport in the membrane separation, and then the momentum balance, and then we need to do a mass balance. So these are all the three key components which we need to deal when we talk about the modeling of the membrane process. So let's say we have identified list of key variables. Let's say if you say a simple FO process, what is interest of our variable? We should know how much concentration I should keep to get the required concentration, how much concentration of the draw solute I need to keep. And then next is that what is the energy consumption if that process is going to be operated. So these are all the two key variables which we need to consider. So correspondingly for that, what are the input variables which we need, that also we should consider, like flow rate of the draw flow rate, the flow rate of the feed flow rate, and then concentration. These are all going to be input variables. Now this phase, capturing this information, normally we call it as a problem definition phase. So when we do any project, this problem definition phase is one of the key criteria. It is like when you do your PhD, like defining a problem for your thesis. If you define your problem by mistake or by wrongly, so what will happen to your whole thesis or whole project? That will collapse. So similarly, if we don't capture this problem definition phase properly, whatever we do further, that leads to a high risk and then low hanging fruits. That's where we talk about the problem definition is very critical component. Once the problem is defined, any engineer who knows chemical engineering, who knows mechanical engineering, will be able to develop a model, because after all you need to do a mass balance and momentum balance. So everybody knows how to do that. And then the one thing which we should look into that, okay, you have developed a model, is this very close to your let's say planned, or it is not very close to a plan. Let's say example, if I'm going to increase the flow rate of the draw solute, what will happen to flex? If I reduce, what will happen to flex? There should be a replica from the actual field, what is happening. So that's where we do that. You try to do a simulation, and then you look for observation data. So we know it may be available in the literature, or you build a small pilot plan and then try to get these observed data, and this observed data will be given to model, and then there will be a simulation environment, and then you try to see how these two are close to each other, and then we know that any model which we assume with some parameters. So there will be some parameters which will be helping us to match the model output with the actual plant output. So we will be estimating those parameters, and that means that the model is capable of predicting the actual plant performance or actual process. So that's where we call it as the validation of the model. This is design phase. And then what we will do, we take that model and then we will try to evaluate, and then we will try to verify with a different process we know. And then once this is verified, if it is having an issue, then it will again go back to a design phase, because there is some need, changes are required, because the model is wrong, which we cannot apply to the process because there is a base assumption itself is wrong. So it goes back to a design phase, where again it will come back with a revised model and revised parameter, and then we can apply this model wherever you need. Like, this is what is basically a model, which we can use it for a design, which we can use it for a scheduling, and then we can use for a simulation and optimization. So now let's take a example of a forward osmosis process and pressure retarded osmosis process, and then let's see how the system can be driven. Now, when we talk about the development of the model, so there are many approaches one can talk about. So how the model you can classify. So how do you determine the form of the model? So what kind of a form the model will be coming out when we are designing a process? So if you see an algebraic equation, so what is algebraic equation? You say y is equal to ax plus b. Y is output and x is your input. This is a simple linear model. But in case if you have y is equal to a x square bx plus c, if it is a polynomial, then also it is going to be an algebraic equation, but it is a higher order model. But these models, we call it as a steady state and also the lumped system model. So where we do not see any other equation. Now, next one is that if you have an integral form, let's say you have y is equal to integral of dx 0 to some say x is equal to xc. Now, this is basically a integral equation where, for a continuous process. So if you have a continuous process, let's say example, you have a tank, the water is flowing from the tank in a continuous manner. I want to calculate how much water is drained from the tank in a 1 hour. So now what we need to do that, we know what is the outflow. We need to integrate the outflow from time t0 to whatever the time we are interested. So this is basically a continuous process where we see an integral equation. So now next is that the differential equation. So what is the differential equation? Where you see dy by dt or dy by dx. So this is, we call it as a differential equation. So differential equation, one, we can have an ordinary differential equation, and then another one is the partial differential equation. So in the partial differential equation, we'll have a steady state and then the distributed parameter. So what is the steady state and what is the distributed parameter? The steady state is, we talk about without dy by dt, then we call it as the steady state distributed parameter. So what is a partial differential equations? We have multiple coordinate. So we say that dy by dx, dy by dz, and then dy by dx. So we can have x, y, z, all three axes. In case of cylindrical, we will have y, r, and then theta. So then we call it as the distributed parameter model. And then the other one is that unsteady state, which is where we have a dy by dt also, and then other three coordinate also. This is, we call it as a partial differential equation. Then when we talk about the ordinary differential equation, so we can have either a steady state one distributed parameter. So what is one distributed parameter? So it's a one-dimensional model, which is steady state. So we will have only dy by dz or dr. The other one, unsteady state lumped parameter. So where there is no distribution, it is a simple continuous straight tank model. So where there is no variation in the coordinates. So where we will see only dy by dt is equal to the RHS. This we call it as the ordinary differential equation. Next is that the difference equation. So what is difference equation? The discontinuous function. So what is discontinuous function? So let's say you talk about all the manufacturing industries. When we talk about any manufacturing industries, where the discrete operation is there, whether 0, 1, or you have a integer or binary numbers. So in that case, we call it as a discontinuous function. And there also we will have steady state and unsteady state, one-dimensional, and then steady state, a multi-dimensional connection, basically a lumped parameter system. So these are all the different types of model which we come across in the chemical engineering domain, or even generally engineering domain. So the adaptation, one of the important aspect which we will be discussing here, that adaptation of the object-oriented modeling. What is object-oriented modeling is that, if you have a one element, let's say you have a model for the reactor, and then you have a model for the pump, and then you have a model for the pipes. So using these components, we will be able to build a plant. So we need a reactor, we need a pipe, we need a tank, and we need a heat exchangers. So you can make any plant, it will not limit. Okay, I can make a process for a membrane separation process, let's say forward osmosis, or FO process, or pressure retarded osmosis, or RO, or even pulp and paper, or steel industries models. Any models can be developed by having a object-oriented modeling approach. So simplification of the model from distributed system to lumped system. This is one of the important aspects. When we have a distributed system, that's going to be a very tough task, and it's a time-taking process to solve. So for example, if you want to apply in a design problems, the accuracy is one factor, but what is the time required versus accuracy? So let's say if you take a simple system, if you plot, one axis is the complexity, and the another axis is accuracy. So let's say this is going to be your accuracy, and this is going to be your complexity. So now when you have high complexity, the accuracy is also going to be very high, but the cost is also going to be very high. So we need to compromise both accuracy and then the complexity, so that the process is going to be optimal, and the developed model can be profitable. So that's where we say that the simplification of the model from the distributed parameter, that plays a very, very critical role, which is very, very important. So now when we want to simplify this model, there are two approaches we solve it. One is the simple finite difference approach if you have a distributed system. And then by integrating a lumped system in series, there are two approaches we can adopt to solve the model. So the finite difference approach we have used, I will be showing an example where we are using a finite difference approach, and then also we are using an integrated lumped system series approach, and how they are going to be beneficial and how we can use for the design application. The easy approach, to develop a 1D dynamic model, it's basically an easy approach. But the problem here is that, the lumped system approach, where we cannot use for 2D and 3D dynamic models. We can use for 1D dynamic model, but we cannot use it for 2D and 3D dynamic model, because we need the finite difference approach. Otherwise, we will not be able to solve them. So now coming to these are the modeling approach which we need to learn, and then we need to develop a model. The next comes to be that the core. Okay, let's get into a forward osmosis process, or PRO, pressure retarded osmosis process. So why we should develop a model? So what is the need of the model? So I said one is that we need to develop a model to optimize the process. So when you say optimize the process, so we should know the characteristics of the membrane. So without knowing the characteristics of the membrane, very difficult to optimize. So if you want to characterize the membrane, there are many parameters which we need to characterize. So for example, pore size distribution, solute and particle rejection, how much rejection that membrane can give. And then knowing these parameters helps to decide whether the given membrane is useful for specific application or not. That is one of the critical things. Now, if you want to estimate these parameters, there are two different techniques which is applied in industry, particularly in the membrane industry. The static techniques and dynamic techniques. What is static technique is that, we don't, use to investigate the chemical and physical properties of the membrane before and after usage. So what is the meaning is that we take out the membrane and then we use some of the instruments to analyze the membrane. So, but in the dynamic technique, membrane is getting operated, but we will be able to predict how the membrane is behaving. So it means that from the pressure, flow, and flux measurement, we will be able to characterize the membrane health or membrane performance in terms of how the permeability is reducing, how the salt rejection is reducing. These are the critical parameters that will help us. So today in this class, we are going to focus how to use the model for characterization of the membrane, and also how do we use the membrane for optimization, model for optimization. So example, some of the parameters, methods like, pore size, we use a bubble point, and then the pore size distribution, we can use, gas and liquid displacement methods. And then permeability, selectivity, and molecular cutoff. So where we need to do an experiment and measure the flux and retentions. And then the membrane structures, we can use SEM, TEM, and FE-SEM. And then the pore size distribution, again, gas liquid displacement method is one of them, is the porometry. And then the functional groups. So what are the different functional groups exist in the membrane that we can use infrared spectrometry? So as I said, in the dynamic method, so where we will estimate some of the hidden parameters. What is hidden parameter? There's basically a model parameter where we call it as the permeability of the membrane and the selectivity of the membrane, which is solute permeability, and then the membrane transport parameter, which is S. Since the active layer of the membrane is dense layer, we see that these parameters are going to be. So what is the difference between the ultrafiltration and RO membrane or FO membrane is that in ultrafiltration membrane, it's a symmetric membrane. The uniformity, the pore size will be uniform across the membrane. But in case of RO and FO membrane, there will be a two-layer asymmetric membrane. So in the asymmetric membrane, the one layer is a dense layer, the another one is the support layer. So that's where we have an active layer, which we call it as a dense layer. This dense layer is going to give the separation efficiency of the process. So let's say if you want to optimize the FO process, so what is to be done? So develop a mathematical model of the process, where we call it as here hollow fiber FO module, by integrating the other peripheral models. So we have so many other peripheral models that needs to be integrated. And then we need to characterize. So what is characterization? Basically, we need to validate the model with the experimental data so that the characteristics of the membrane will be known to us. Then optimize the hollow fiber process to meet certain objectives. We will see what are those objectives which we need to consider for forward osmosis process. So this is what is the process. So we need to do an experiment where in this experiment, what will happen? The water from the dilute solution will be reducing, and then that will be added into a concentrated solution. And this will continue till both sides the salt concentrations are going to be equal. Now you see here there is a two layers. One is a support layer, another one is active layer. So what you see here is that the active layer facing the draw side. So we call it as the active layer. This is active layer which is facing the draw solution side. Also we can use the active solution facing the feed side. So when we will use active solution facing a feed side, when we will use active solution facing draw side, it will be depending upon whether your feed is dirty or your feed is very cleaned and free treated. If your feed is not dirty and if it is cleaned, then it can be exposed to a support layer. But if it is not cleaned and if it is a dirty, then we need to expose to the active layer. So that is depending upon that one can choose. The another aspect, if you talk about the hollow fiber module. So when we say hollow fiber module, these fibers are assembled in such a way, and these fibers, if it is very small, and if you pass, let's say, highly fouled content, so what will happen that the fouled content can choke the fiber lumen side. That's why we prefer the low fouling content will be passing through the fiber lumen side, and the high fouling content can be passed outside the fiber. So this is one way of making a process fouling trouble free. The next one is that experimental procedures. These are all you can find it in many literature. However, a typical experimental procedure. There are two types of experimental procedures one can follow for forward osmosis. One is a continuous process. Another one is a batch process. If you want to do a continuous process, there will be a huge requirement of what we call it as the draw solution and feed solution. So example, if you are running a plant, the membrane with 100 liters per hour, if you want to run an experiment for even a half an hour, we need 50 liters of feed and 50 liters of draw solution, and that's going to be very, very expensive process. If you want to do a multiple experiment with multiple concentration changes and then the temperature changes, that is not going to be viable, which leads to a huge consumption. Then another approach in the same way, if you have some regeneration process. What is a regeneration process? If you can regenerate the draw solute, so where you concentrate again the draw solute using another process, then you can run it in the continuous process, because the concentration is also requires the huge expensive operation. So many of the experiments are proposed to do it in the dynamic modes, which is batch mode. So what is batch mode? The draw solution, which is concentrated solution, is supplied through the membrane, and then again it is coming back. If you look here, this is supplied in the cell side, and then from the cell side again it is coming back to same vessel. So it means that it is getting recirculated. So what is the meaning? When it is getting recirculated, so what will happen to the draw solute? It will get dilute over a time. It's at time t equal to 0, the value may be 50 gram per liter. When time t is equal to, let's say, 10 minutes, the concentration will reduce to 20 gram per liter. So the concentration of the draw solute in the tank will be varying with time. Similarly, if you look at feed also, that is circulated through the fiber and it is coming back to the same tank, wherein the feed concentration will be increasing. Why? Because the water is transported from feed to draw solute. So the feed concentration will be increasing and the draw solution concentration will be reducing. So we need to maintain a constant temperature. So we have a temperature maintenance unit, so that will take care. And then we need to measure the concentration, conductivity, all parameters which are going to vary with time to make sure that. So this is a typical commercial module available from Toyoba. These are the specification. It's approximately half a meter length, and then the diameter is around 7.5 centimeter. The material is cellulose triacetate. The membrane material is cellulose triacetate, and the cellulose triacetate is basically a asymmetric membrane where the support layer with a high porous structure and then the dense layer are also cellulose triacetate. This is basically a hollow fiber module. The module has the huge number of, around 99 into 10 to the power 3 number of fibers, more than around lakh fibers. And then the fiber inside the diameter is something like 85 micron, which is like our hair size. So our hair size is something like 175 micron. So coming to a model, what is the objective of this model? The objective of this model is that, we need to develop a model that will be capable of predicting the output draw solute concentration, and then output feed solution concentration, and then flow rate of both draw and feed out. So that should be the objective of the model for a given input conditions. So how do we do that? How can we achieve this? So one is we need to do a water balance. Another one is solute balance. Now question comes is that this model is basically a steady state model. We are not looking for a dynamic model. The reason is very simple. The model which we are using in this is a very small capacity. So this small capacity requires residence time very, considerably very less. So that, we are trying to simplify the model as a steady state system. So how do you model this complete unit? We need to take a single element. So this is basically a single element, and we need to make an element balance. So what is the element balance? So the water is passing through the tube, which we say that tube side, and water which is passing in the cell side, which we call it as a cell side. So now the water balance will be there for draw side and feed side. So if you look, the draw solution is passing through the cell side. So where the cell side is balanced with this. What is the cell side is balanced? Input minus output is equal to the accumulation, or plus generation is equal to accumulation. So accumulation is 0. There's nothing is getting accumulated because it's a constant volume. Okay. So the density is going to be constant for the solution. It cannot vary. So the input here is that the QDS at n plus 1. Okay. So we are coming from here. This is the input. And then the minus QDS which is going to be output. So now n plus 1 is going to be output and n is going to be your input. So input minus output plus this is going to be the water which is coming from the draw side to the feed side. Okay, so feed side to draw side. So because feed is getting concentrated, so the water will be coming from the feed side. That's why we have a plus JW. What is JW is that the water flux multiplied by the surface area of the membrane. So which gives you the net amount of water is flowing from feed side to draw side. Similarly, if this much amount is flowing from feed to draw side, that means that again this much amount of leaving from the feed side. That's what this is input minus output, and then again minus of this volume is equal to 0 because there is no accumulation. And then we have a solute balance. So what is solute balance? So similar to water, the salt or draw solute also will be traveling or transporting through the membrane, and that transportation is defined by using a solute mass balance. So what is solute mass balance here? We have the input. What is input here? The QDS multiply with CDS, which is concentration of the solute and flow rate. You will get the kg of solute passing to the element, and then the minus of whatever this is going to be minus whatever is going to be multiply this. you get, it's going to be minus. And this will give you the salt which is coming out of the process. So how much salt is coming out of the concentration of the salt which is coming out of the finite element. Similarly, for a feed process also, where we have the water which is coming out. This is a water balance, and then what is happening here? It's a batch process. So in the tank, the water is going away, and then water is coming back, either draw solute or feed solute along with solute. So how do we model that? So we ds at time t minus at time t plus t. So you have time t and then next time, which is equal to the accumulation of the solute is equal to the difference in the flow rate, the net change in the flow rate, inlet minus outlet. And then similarly for a feed also, we do a tank mass balance, and then we will get the overall balance, which is delta V. So how much volume is changing for a given interval. And then similarly, we apply a solute mass balance. We substitute the other equation. So we will get the solute mass balance from this equation, again, CFS N and then CFS, which is T plus T for this particular concentration. We just need to make a salt balance. So if you look, these equations are discretized applying a finite difference method. So what is finite difference method? So if you talk about this particular equation where we are writing about the Z direction, there is a variation in the Z direction, and that is getting discretized for every single element. Okay, that is the meaning. And then in this equation, so what is unknown? So the JW is unknown. So we need to calculate what is JW. So to calculate the JW, we have membrane transport equations. So what is this membrane transport equation is that we have a concentration polarization in the support layer and then the mass transport in the active layer. Now, using a concentration polarization model based on the film theory, so if we derive it, we will be able to get the water flux through the membrane. I don't want to give into more detail. If somebody is required, I have kept as a slides in the annexure that can be used for the derivation. And then similarly, the solute flux, where salt is also flowing from the draw solution to feed side. So that JS is also can be derived using this concentration polarization theory model, along with the membrane transport models, which we call it as the solution diffusion model. Now, the next is that if you look in the module, so one is the change in the concentration where you do a mass balance, you will get. Next is that the variation in the pressure. The pressure is going to vary along the module. So now how do we vary this pressure along the module? To calculate that pressure drop, we are moving into a pressure drop equation where the dP cell by dz, which is a differential equation, and this differential equation is going to give us the pressure drop across the cell side. This is a typical equation which we use for a packed bed, which we call it as a Ergun equation. So if we know the porosity, diameter of the fiber, and then if we know the viscosity of the fluid, we will be able to calculate the pressure drop for a given velocity of the fluid in the cell side. And then similarly, we can calculate in the lumen side, which we call it as Hagen-Faschel equations, where we use the flow through the pipe where we can estimate the pressure drop. So now the question comes is that model is ready. So we have derived the model equations. So how do we use this model for a validation? So now we need to perform experiments where these experiments going to give actual measurements from the sensors. For example, the concentration, how it is varying with time, and then the concentration of feed, how it is varying with time. And then the experimental conditions. So what are the different experimental conditions and then corresponding output. So we are going to use the volume of 4.2 liters, and then the in the tube side it is 10 liters. Okay, tube side feed solution. So why feed is very high volume? Because the water will be transported from feed to draw solution side. And then the concentration, so we are talking about the sodium chloride as a draw solute, where we have used 45 kg per meter cube, which is equal to 45,000 ppm. And then this is 30,000 ppm, which is equivalent to seawater. And then we used a feed flow rate, and then around 1.7 liter per minute, which is equal to around 100 liter per hour. And the draw will be 100 per liter per hour, and then feed solution is 2.7, which is around 180 liter per hour. The pressure, as I said, forward osmosis, we don't apply a high pressure. So both sides is, almost equal pressure, which is around 1.3 bar and 1.2 bar, which is normal pressure for membrane separation process. And the temperature of the solution we maintained around 25 because our interest was to keep it at constant temperature using a temperature bath. So Ergun equation, is one of the equation used for a packed bed pressure calculation. But if you look system where we are using when you are compressing the fiber, or if you are pressurizing the you have a porous media. The Ergun equation is applicable for non-porous media, but here it is a porous media, so we want to recalculate the coefficients of the Ergun equations, which was used E1 and E2, where we have used a simple pure water and then calculated the pressure drop. Using this pressure drop, we were able to calculate what will be the parameter of the E1, E2, wherein we just manipulate the error by calculating from delta P experimental minus the delta P modified Ergun equation. This is going to be a modified delta P Ergun equation. So once we calculated the Ergun equation coefficient, so we are planning to calculate the other parameters, which are like water permeability and solute permeability. Now, what we observe from the literature and also from the experiment, the water permeability was observed to be constant, but however, the solute permeability, which is varying with the concentration of the draw solute. So what is solute permeability? So in our equation, if you look, the membrane transport equations, where we are using this coefficient A, this is going to be a water permeability coefficient. And then we are going to use a B, this is going to be your the solute permeability. And this is membrane structural parameter, which is S. These three parameters are unknown for a given membrane, and that needs to be estimated always before applying the model for optimization. That is one of the main critical requirement for any membrane separation process. We need to estimate the water permeability and solute permeability. In case of FO, we need to estimate the membrane structural parameter, which is S. So we observed the solute permeability is varying with respect to concentration. So because the diffusivity of the salt is going to vary, the salt in the solution is going to vary with respect to the concentration. So from that angle, we also found to have it is constant for some concentration. After that, it is reducing. When concentration is reduced, the solute permeability is reducing. So to incorporate that, we have brought a equation which is B is a function of the concentration of the draw solute. However, after some C star, it will be constant. That's what we are seeing. It is constant. So we need to estimate both C star and also the M and B naught. This is going to be a critical requirement. And then the other parameters like, the Yergin equation parameter that was estimated, using pure water permeability data. And then the mass transfer coefficient, when we use a film theory, so we will have a mass transfer coefficient for the system of equations. So example, the KFS and then the KDS. These are all the mass transfer coefficient for the cell side and the tube side, which is draw side and feed side. So these parameters are estimated by using experimental data. So where you can see that we were trying to minimize the error between experimental versus model. So if you see, the experimental is a dotted line and the continuous line, and model is a continuous line and experiment is a dotted line. So where both are trying to match closely for a concentration and also the net volume. As we know that the volume change in the volume in both the feed and draw solution will be increasing. So that's what we are seeing here, that net volume is increasing. And then what will happen to the concentration of draw? It will be reducing, and then the concentration of feed will be increasing. So that's what 45, it is getting reduced to 25 in 200 seconds. And similarly, the feed solution is increasing from 0.5 to around 1. So this is what is the dynamic process, and then how we can tune this dynamic process model. So next is that, you can see there are many literatures, and we have compared this parameter, and which is coming to be very close to what is reported in literature, but some parameters are not matching, but that is maybe, due to the model accuracy. That's what we are talking about. The model accuracy is also plays a very important. If your model is more complex and accurate, the parameter what was reported earlier is not going to be same, because the uncertainty in the model is getting accumulated in the estimated model parameter, and that also needs to be considered. Now, once you develop a model, so what we need to do, that one has to establish the simulation study. So why we need to do a simulation is that, why we need to simulation. So to study the performance of the process before conducting the experiments. So we manipulate the variables which are, considered to be, manipulated to get a optimal process conditions. Example, the inlet flow rate of the draw solute, and then the feed flow rate of the draw solute, and then we manipulate the length of the module, because the pressure drop is going to be a critical parameter that will lead to a higher energy consumption. So length also can be optimized. So the assumption, when we are going to manipulate these, for example, when you manipulate the length, I need to ensure that the membrane surface area is available is going to be constant. So how do you make them? So when you are manipulating the length, automatically the diameter is going to change and the porosity is going to change. So what does it mean? The number of fiber is going to increase, and then the diameter of the cell side will increase. So what does it mean? So let's say you have a module with this length, and that becomes, smaller diameter, then the diameter will increase, and the number of fiber is also going to increase in this. So where both modules are expected to give a similar performance, because the membrane area is equal. The amount of membrane used to fabricate that module is same. Let's say this is membrane 1 and this is membrane 2. This is membrane 2. but both are going to satisfy S2. So the area of the membrane is going to same, and the porosity of the packing density is going to be same. So when we try to simulate this process, so how the response looks like. So when you increase the feed draw solute flow rate, so we see here is that there is a huge increase in the net permeate flow rate, and then with respect to feed flow rate, there is no much change observed. It is almost constant because the driving force is not going to change. So that's why we are finding no effect, there's no big effect on feed solute flow rate, and then the draw is having a very huge impact. Now, when we talk about the power consumption, because when both flow rates are going to increase, we know that the power consumption is flow rate multiplied by the pressure drop. So since the pressure drop is almost constant, where flow rate is increasing, you can see that this point is very low energy consumption, and this is going to be very high energy consumption. So now we can decide which is the best operating point for a given production capacity. And another aspect, if we look, this is the permeate is varying anyhow, and if you take energy per unit permeate volume, so which is very important, how much water is produced is one factor, but the other side is that how much water per unit energy consumption. If the energy consumption is huge, then also the process is useless. Even though you can get a very high volume of water, that doesn't mean that process is superior, depending upon the scenario. So this is what the observation, the increment in the net permeate flow rate is due to the less DS dilution. So that's what, when you increase the DS flow rate, so we are finding higher flow rate. That is basically because of the less dilution of the draw solute. And then the effect of feed flow rate is almost negligible. That's what we have seen. So the next plot, which we are seeing, how module length is going to play a critical role. Module length is going to play a critical role. So similarly, you vary the draw solute. Yes, we have impact on it because the feed flow rate was not giving any impact. That's why we have removed the feed flow rate with module length, and then we can see that how the contour looks like. So if it is a QF is going to be 3 liters per minute to maintain a sufficient feed flow rate inside the module, because if you don't maintain a sufficient feed flow rate, what will happen that there will be a lag in the process that will result in other complications. These are all some simple ways to understand how the system is performing. So now once we know the system performance, if you look, so what is happening? The power consumption is increasing when you are increasing the draw solute. But however, we need to look what is the optimal point, at what draw solution flow rate, at what module length we can get the maximum output profit. So we have two objective functions. One is we need to minimize the power input. The other one is that we need to maximize the permeate flow rate, because both are important. We need to meet the target production, and then we need to minimize the energy consumption because process should be profitable. So how do you calculate the power input? So there are two pumps will be supplying the fluid to the FO. One is draw solute, another one is feed solute. So we multiply the pressure, multiply with flow rate. If it is a Pascal and if it is a meter cube per second, the unit will be watts. So that's what is this many watts is consumed in the pump. So when we add both draw and feed pump, we will get the total energy consumed in the pumps. And then we have a product flow rate where we can calculate from difference in the draw flow rate or difference in the feed flow rate. Now, from our simulation, we can conclude, this is the limit we can fix for all our decision variables. So what is the decision variable here? So we say that the length of the module, pressure drop across the cell side, and then the pressure and then we have a QDS and then QFS. The penalty functions, so what is the penalty function here is that to ensure, module is operated at positive pressure and positive flow. So what happens that if you are giving very low feed flow rate, at some point the water flow, feed flow inside the module is going to be zero. So to avoid that, we should give a sufficient and more than enough feed flow rate, which is QFS greater than or equal to 0 at the outlet. And similarly, the pressure at the draw section, okay, that is also should be greater than 0. It cannot be less than 0. And then pressure for the feed also should be greater than 0 because, outlet feed, if it is less than 0, then water will not come out of the module. So this is going to be the penalty function in the objective function. So we will add that as a penalty function in the objective function. And then also we need to make sure that the strict FO condition. So what is strict FO condition? If you remember the first slide, if you don't apply any pressure difference across the membrane, then it is FO. But if there is a pressure difference, if you apply a pressure at the feed side, then it's a pressure assisted osmosis. So we don't want the pressure assisted osmosis or PRO. For that, what we are saying that a PDS inlet is going to be higher than the PFS inlet. So it can be either a FO or pressure assisted osmosis, but it cannot be PRO. The model equations are going to act as an inequality constraints. So now, by using standard optimization techniques, either use a GA or a particle swarm method, so we could get the optimization. So what is the optimization? So maximize the cost QP and then minus the energy cost. So this energy cost, is going to vary with respect to region and market. That's why, multi-objective optimization is very important. So that generalized solution is available. From this generalized solution, one can choose which is the location he would like to operate or he would like to design the process. So what is the multiple Pareto we got it? So if you look, the permeate flow rate versus the power output. So how much power is consumed? So that's what we are defining here. This is one output is QP, another one is PW. So that's what, if you see here, it is increasing as you increase the permeate flow rate. But after some point, it is exponentially. Okay. So this is one of the important observations which we need to consider while designing the membrane separation process, particularly FO process. And then similarly, module length also we have the, and then the draw solution and feed solution flow rate and how it will vary with respect to permeate flow rate, and then draw solution, feed concentration, and specific energy consumption. If you look, the specific energy consumption is also conflicting. When you are increasing the permeate flow rate, specific energy consumption is increasing because we need low specific energy consumption. At the same time, we need a very high permeate flow rate. But that is not happening, which is conflicting. If you try to increase the permeate flow rate, the specific energy consumption is trying to increase. But at this point, some extent it is constant. Similarly, here also power. That's why we call it as this is a conflicting objectives. So where we can define the system. So again, same thing. If you look at recovery also, the recovery is another critical parameter where you see here that it is constant around this point, but otherwise it is very low in this side, and then so the upper end very low. We should ensure that we are defining the recovery around this area so that neither will go on that side or this side. Yeah, next is overall conclusion. Whatever I have summarized, that is basically a conclusion. So one can use the optimal Pareto to design the FO process. Similarly, we have used earlier one is a Toyobo membrane. This is a aquaporin membrane. Now the question comes is that we have used a finite difference method. The approach we used is a finite difference method. Here we are going to use the lumped system approach. So what is lumped system approach is that we can develop each element as a single unit, and the single unit can be connected in a series, and that will give you a similar model. But this is very easy to implement, very easy to execute, and of course, you need some dedicated tools. Before going into detailed about this, I would like to have some question and answer section for the whatever we have covered, the finite difference method. Any questions?
So what was the simulation tool that you used? It is MATLAB, right?
This is the MATLAB, and also Dymola we are using. So where you can use the Mathematical is available as an open source, which you can use.
Mathematical, you're saying, right?
Mathematica, yeah. But these are all, not that complex. If you know finite difference, you can use even Python also. Platform is not a restriction; anybody can use.
Actually, in our lab, we do a lot of experiments on membrane separation, basically arrow filters, but there is no simulation and modeling. So I was a little interested in this part because in our lab, that is totally experiment based. So
okay. So you can take some of my students. I will be giving who are working in this. Maybe you can take their help.
okay.
Yeah. Who else? Any other questions? Okay, so if there is no questions, let us move to the next one. Is more about how do we model the same system using an object-oriented approach. So if you see here, each one of them is going to be act as a lumped system. So we can connect this lumped system in series, and that is also going to act as a distributed parameter. But if you have let's say two axes, let's say x and y are y and r, then it's going to be a problematic. Then we cannot use this lumped system approach to model the complicated stuff. So here also, similar way, it is more details is given how the concentration is going to vary. So and how you can capture this model. So example, this is we call it as a FO mode. So what is FO mode? Is that the feed solution is facing to the active layer. So what is feed solution active layer? Wherein the feed is more contaminated, it can foul the other side, which is a support layer. For that, we are using a feed solution facing the support layer. And then we call it as a PRO mode, where the feed solution is facing where we pre-treat, and it's a pure water, so it will not foul the membrane. So, but the draw solution, there is a chance there's a seawater that can damage the membrane if we put it in the other side. So, as I was telling you, we need to use solution diffusion model and then film theory to capture this concentration profile. So what will happen to the concentration? Because of dilution. So here the concentration will be high. Since water is transported from the feed side, there will be a dilution in this place. So that because of dilution, the concentration will be low. And similarly here also, because of dilution, the concentration is getting reduced. So how to model this concentration profile and how to model this? So for this, we are using a solution diffusion model for the membrane, and for the concentration polarization layer, we are using a film theory, which is widely adopted in the membrane modeling process. So the another membrane which is available for forward osmosis is basically a aquaporin membrane. So we have used this aquaporin for both sugarcane juice concentration and T concentration. So here you have a detailed derivation for what I was explaining earlier. So the membrane transport equations, how you will be writing it. So the JW, so the flux, you can write it as a flux multiplied by the concentration osmotic pressure difference, and then we have a delta P. So that's what, again, you have a JS, which is a solute flux, where difference of the concentration. So, and one of the important thing is that when we have this membrane, we always say that the draw solution is going to diffuse to feed solution. What about the feed solution diffusing to draw solution? So normally when we have a juice application, the molecules are bigger size, so they cannot cross the separate layer. But if you talk about the sodium chloride, the molecule is smaller size, they will pass through the separation layer. That's why we expect the reverse solute flux, which we say that the NaCl is going in the reverse direction. So we call it as a reverse solute flux. But if the T, if we are using a T solution as a feed, and if the T components are going to a T's feed to the draw side, then we call it as the forward flux. So what we are assuming here is that the forward flux of the T component is 0, and then we also observed experimentally it is 0. So this is a reasonably a good assumption in any FO process. If the high molecular weight, they will be stopped and it will be 0. And the osmotic pressure is calculated using a standard 1/2 equation. And this is, there are other models that are also available that can be used. Right now, my student is also trying to develop another model for, T solution. Whatever the osmotic pressure is reported for sodium chloride can be adopted, but for T, there is no reported data. So she is trying to develop a model for that. And when we talk about the mass balance in the film, so this is a standard film theory model, the net flux of sodium chloride, which is passed from the draw solution to feed side, where you have one is the diffusion phenomena, another one is convection phenomena. This is a convection term and this is a diffusion term. The diffusion term will lead to forward further, and convection term will try to push, because from the feed solution is trying to come to in the opposite direction, that result to a convection phenomena, and there is a concentration difference that will result in a diffusion phenomena. So if you solve this equation with appropriate boundary conditions, so you will get what is the boundary condition, x is equal to 0, what is the concentration, and x is equal to Ts, what is the concentration. So you will be able to get the concentration of CDM. So if you know the CDB, you can calculate the CDM, wherein the KD, the mass transfer coefficient, is going to be a unknown parameter that needs to be estimated. And then similarly, we can estimate the concentration at the CFM and the CDM by knowing the KF and KFT. So this is also, again, you need to integrate with the known boundary condition. So now the model parameters are, as I said earlier, solid permeability, hydrodynamic water permeability, and then the structural parameter, and then mass transfer coefficient. So what we try to do that in this process, this is a set of equations where we have parameters, and then the mass transfer coefficient is defined in terms of, Sherwood number, Reynolds number, and Schmidt number. So we will calculate the alpha and beta values from the experimental data. So in the model, so what is the simplified model here is that, same equations, but, we don't need to write it in the finite difference. Here we are writing a simple lumped system, where in this lumped system, QF in minus QF out is going to be equal to the whatever the flux which is going away. And then similarly, in the concentration, the solute concentration is a mass balance. The kg of salt going in, kg of salt coming out, in minus out, and then this is going to be the whatever is coming from the draw side. So similarly, we can do for a feed side and draw side. So you will get the mass and energy balance, mass balance, and then we can go for the tank mass balance. Similarly, here also it's an unsteady state process where we can write the mass balance for the tank. Accumulation of the volume is equal to QF in minus QF out, and similarly the accumulation of the salt, we can write VF into CF, wherein we are assuming density is not varying. Okay, the density is constant for input and output. Similarly, here also the density is constant. So how to implement this model? There, you can directly apply a finite difference algorithm where you need to do multiple for loops, and then converge the problem, and then you can get it. But in this case, it is very easy. There are standard solvers are available which we can use. So for development of 1D mathematical model, there will be n number of continuous street tank. It's basically a completely mixed tank unit where connected in series, which is assumed to be equivalent to a flood flow. That's what we will be doing it here. So what we do that, we will be connecting multiple in the counter current mode, because our co-current mode, whatever the experiment we do, that we will be doing. Now, how many numbers we need to fix, that is a critical question. So we need to do a grid independency test. So you increase the number of CSTs, and then when the number of CSTs are increasing, there will be no change in the output. We are getting a consistent output. Then we can say that where we are having a consistent output, say starting, that is sufficient enough, because if you increase more number of CSTR, the number of differential equation is going to increase, and that will result in a computationally complex problem, and it will take more time to solve them. So in a pictorial way, if you look how we are doing, so we are making a CST1, CST2, CST3, and they are connected in series, and then along with the tank, and then we are trying to calculate JW experiment, and then JS experiment from the model, where the salt flux and the water flux. So having this, so then we will get the experimental data, which we will get from the data, and then we try to manipulate the model output, and then try to estimate the parameter by manipulating the feed flow rate and the draw flow rate. So the similar observation you will get. Now the question is that, I'll give you a simple idea here. The team who did this particular modeling, she was not knowing MATLAB. She don't have much experience on the coding, but still she was able to develop the model, and she was able to implement. Only that she knows how to do a mass balance, how to do an energy balance. So if we can do a object-oriented modeling, even a person who doesn't have a computer science knowledge or coding knowledge, they can implement this model in an easy manner, and it can be used for design of any process. So this is a effect of major T component. How the T composition is going to change. We have the multiple component of T, like EGC, and then EC and caffeine. These are all the main components present in the T, and that will be increasing with time, because we know that this is going to be a concentration process. While removing the water, this concentration will be increasing. So we found that it is more viable, and it can be piloted. The only problem we found that using a salt leads to a reverse solute flux, and that's creating a problem in the taste. So to avoid that, we will be using some innovative draw solute. My student is working on right now to develop an innovative solute that will help us to concentrate the tea without compromising the quality. So these are all the observations where we need to manipulate multiple parameters, and then how the solution is going to change with time. So then also we can change change the direction, active layer facing DS, or active layer facing FS. That also has a significant effect, and then you can optimize depending upon what is your system. So this is available as a literature, and it is published. I will be giving you in my slides those manuscript. I mean, you can read this manuscript and you can understand. If you have any doubt, either you can approach my students, and then I can also present. So overall, what I would like to tell you that these processes, in a way that very important to analyze the system with appropriate model, and then go for optimization, and that will help us to design a process in an effective manner. And that design process can be implemented in the actual plant. Okay, this is one of the critical requirement one has to satisfy. This is another application. where we have used sugarcane juice for concentration. So, yeah, pardon? Any? Okay, so similarly, we have also used sugarcane juice, and then we have tried to see how the solute flux and then water flux and then the sucrose concentration will increase. So if you have a successful process for FO, then the crystallization of sugar using a forward osmosis is viable, and that is more beneficial than any process currently we have. So similarly, you can manipulate many processes like water flux, and then you can calculate the parameters, and then you try to analyze the problem in a better manner. So now the question is that here also we observed the salt concentration is going to be a critical phenomena, and that result reverse solute flux is very high when you increase the CDS. So identifying an appropriate draw solution is going to be a very critical and very important for designing a FO process. So with this, we went for a fouling study, and in the fouling study also we come up with a smart mechanism. How do we clean this membrane, and then how we can do that? Right now we are focusing on how to develop a model for the fouling phenomena also. And we found that pre-treatment of the juice is one of the critical requirement for designing the FO process. If you design a appropriate process, then we will be able to get a more meaningful process. So this is what I would like to stop here, and then I would like to have a quick discussion, and then if any input is required, we can discuss. So this is what is about design and then optimization using a mathematical model. Rajkumar, you are in line.
Can you hear?
Yeah, I'm able to hear you now. So I would like to have more discussion, so that, it will be more useful. I see there are 32 people. So more discussions can give, better insight about the process.
So, any questions from participant sides, they can ask actually. They can turn on their video and they can ask. And hello?
Hello, yeah, please.
So in case of this membrane, actually, do you need some sort of the strong supports?
The one of the
Just like in case of polymeric membrane.
Yeah, see, the main difference between the conventional RO membranes and FO membrane is that the support layer. In the case of RO membrane, the support layers are highly dense, and that results in high internal concentration polarization. So in this case, we need a thickness should be very low, such that the internal concentration polarization is very, very optimal. It should be very optimal, so that the net driving force available for water flux can be maximized. So most of the research nowadays is focused on developing membrane that will be having a smart support layer with a dense support layer. Even the support layer porosity and thickness is a very critical parameter. And yes, support layer is very critical for FO.
Yeah, because I also make some polymeric films, and this sometime I got the membrane type of film. But how to quantify those fluxes actually? Uh,
See, there are standard test cells are available, which we can use it for. See, the question comes is that first thing you can analyze the pore size and pore size distribution. So from SEM or FESEM, you can come up with an, let's say, the pore size distribution. If it doesn't have any pores, then we cannot, consider it to be a support layer. But for separation layer, we may not be able to see the pores, but still it is a diffusion phenomena. But it is very, very, teeny, something like in a sub-micron level, in a nanometer level. The coatings are in the nanometer level.
mhm. Somebody wants to say actually, Miss Noni something. We have actually one more participant from Bangladesh, Dr. Safruddin Jaman. Hello, can you hear?
Good morning, sir. Actually,
Hello.
directly in the morning I could not join. So later I was little bit net connection problem. So I
See,
joined
sometimes
later.
people's
So
mic
I'm
doesn't work.
attending the
So,
course.
so,
So
so
when
whoever
when
have some mic
later,
problem, they can type their questions in chat box. Uh, that's not a problem actually. That's good. Hello. It was not clear actually. Again, the connectivity may be the problem. Uh, the participant can type their questions there actually, so I can read and he can answer from there. If I think there is no question from participant side, so you can conclude or we can finish it up. Dr. Jales, you want to ask something?
No.
Yeah, because I found your raise the hands up actually, so I thought you want to ask something.
No.
So how many are from industry?
So okay,
How many are from industry? Who
the
is participating?
industry people.
From which industries?
This time industry size actually. Let me see who is there. One is there. Mostly are from academic actually at present in this session.
Okay. Okay, so if anybody wants to have input on this, this is my student's profile. They will be able to help you if any research inputs are required in this topic. So let me share the screen. You can approach. Yeah, I would like to also acknowledge them. Haptam is my PhD student, and Dinesh is also my PhD student. So they both worked on design and optimization of FO, and they have a good strong. And then Ananya is working on the T concentration, and then Anisha and Mantip, they were working on sugarcane juice concentration using FO. So Mandev is with Cadila now. He's working in the Cadila. So you can get their email ID and other details in the website and also in the manuscript. And you can get my Google Scholar. You can refer all the manuscripts which are relevant to this topic. Okay. But there is no question.
Yeah. Actually, if there are no questions, actually, so we can end up this session here. So I would say thank you very much once again to be the part of this course and managing the time for this. And it was I missed actually some of them because I have to go to some meeting. So it was a good thing actually. Lecture people have understand what membrane separation processes are, as well as how to model them, how to solve them, and various industrial applications. And these peoples and everybody would be benefited from that actually. So with this, thank you very much. And our next session would be at 1 o'clock. There we will have Dr. Bimal Kumar from IIT Roorkee, and he would be talking on polynomial fitting of actually experimental and data. So that would be the next topic actually at 1 o'clock. So
Bye.
with this, yeah. Do you want to say something, Senthil?
Yeah. Bye. Take care. Bye.
Okay. Bye. Thank you very much. Bye.